Let's go to the example now in your lesson for 3.1. And in this example, we have a data set over the course of 6 terms or 6 years of a professor tracking their final grade for their first year stats classes. And you can see the size of the class versus the mean final grade of each of those classes as well. And we want to see is there a correlation between class size and mean final grade? So when data is written in this horizontal fashion of one variable listed in the first row and another one in the second, it's really important to note that the first row is always the independent variable. It's always the one that goes on the x-axis down here. And for consistency's sake, the second one is always the y variable. And this should always be the case. And that way there's no ambiguity in terms of which is the dependent variable, which one's the independent variable. Okay? So in order to take this and to graph it on the graph paper that is provided on your note, I've just drawn a sketch here. Our first thing is to figure out how to spread out this data so that we don't necessarily have to start at the origin 0, 0. And it doesn't make sense here that we would because we really want to zoom in on this section of data. So what I'm going to do is I'm going to show that this is going to be a broken graph in both directions and that we are not going to start at 0, 0. So let's look at a range for each of these. If we look at the x range, we can see that our smallest value is 62. Sorry, I missed a set in here, I think. I did. Let me add it in. There's a 62 in here, and there's a 69 in there. There we go. That looks better. All right, so the lowest or the smallest value is 62, and so here's where we want to start, 62 ideally, or close to it. And our largest value is at 145. So what are we going to have to stretch that range over in order to figure it out? Well, we realize that 145 minus 62 means that we've got a range of 83 that we have to spread out over the number of squares that you have. So I've done a little bit of work for you ahead of time, and I've realized that if you start with the first square in your note at 60, and if you go up by 5s, you will enable yourself to be able to fit that range of data all the way across to 150. Okay? So again, this is a bit of a rough sketch. Yours can be more accurate. Take a moment to fill in your x-axis so that you end up, and I'm just going to do one of these for now, you will end up at 150 with an extra square left over likely in the space that I provided you with on the note. Okay? In similar fashion, we should look at what the range for the y values is too. So the smallest value we have to plot is 61 right here, and the largest, actually here and here, it's twice, and the largest value that we have to plot is 70 right here. So the range of values that we have then to spread this out over goes from 61 up to 70, which is a range of 9. And again, I sort of planned this ahead of time in your note. If you start on the first square up at 61 and you go every other one, in other words, if you go up by halves, you will end up all the way up at the very, very top, reaching 70. Okay. Then I'd like you to pause the video for a moment. I'd like you to plot the points. You're going to be able to be far more accurate than I because you've actually got grid paper. I'm going to just sketch more or less where the points end up relative to each other. And again, mine is super rough. Yours can be a lot more accurate than that. So when you look at your scatter plot, and it comes out sort of like this, in part A it says, does a scatter plot of this data indicate that there could be a linear relationship between the two variables? Well, if you take your old-fashioned way of doing things and you line up a ruler, you and I might decide that the angle should be slightly different, and therefore, in old-fashioned ways, we would end up with a different slope, which is always troublesome, but it was satisfactory when you were in grades 9 and 10, right? Again, I'm just going to make a rough line with what I have. I'm trying to get, maybe three dots close to being on a point and spreading out the others. And you could take a moment and draw in what you feel is your best fit line. But what if we could actually find this best fit line using electronic tools, but then also using the calculation of R? And the answer is we positively can. Now off here to the right, you'll see the equation for calculating the correlation coefficient. It is not a pretty equation. You never have to memorize it, but I will show you how it works. The best way to show how it works is down here in part B at the bottom of your page, is to take this chart and turn it this way. And again, when you, in future classes, set up a table of values and you do it vertically instead of horizontally, you should always put the x variable first and the y variable second, so that that is always consistent for your reader. They always know how that should work. Now, if I go ahead and I fill in all of the values here that you have up above and making it in a downward fashion instead, we can do a lot of the work before subbing in here in this table here. Let me show you what I mean. So one of the terms that's in here is something called x squared, and you will see it right there. Another term is just the sum of the x's. That's this one. You'll also see one that says the sum of x times y for each data point. That's this one. You'll also see the sum of the y's right there, and you'll see the sum of the y squared values, which is here. There are 5 different summations or summation values that have to go into this equation. So let's figure them out independently. So what I'm going to do for the x squared column is exactly that. I'm going to take the x values, here, 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 and here, and I'm just going to square them in your calculator. So I'd like you to go ahead, you can pause the video, go ahead and fill those in. You can unpause and see if we match. You can do the same thing for the y squared values, just take each of these y's and square them. And then similarly, you can take each x times y, a coordinate pair, multiply them together, and put the values here. Go ahead and pause, do all of those, and then add them all up and put the summations down at the bottom, and then we'll see if they match. I'll draw them in quickly while you're paused. Okay, I elected for the sake of time not to fill in the remaining values because I think you're more than capable of doing so. But what I am interested in then is all these final answers. So the sum of all of the x values for my data set is 733. The sum of my y values is 457. The sum of my x values, each squared and then added together, is 82,857. I've got my y squared values here, and then I've got my xy values here. All right, so what I'm going to do is I color-coded them so that we can see how they fit into the equation above. All right, one variable I didn't talk about yet is this value n. N just stands for the number of data points or coordinate pairs in this set. So altogether, you can see that there are 7. So we can plug in a 7 there. We're going to multiply that by the sum of the xy values. Those are these guys right here in purple. So I'm going to put in 47,169 here. I'm going to subtract from that the sum of the x values. That's the one that's in pink. So that is 733. and I'm going to multiply that by the sum of the y values, which are in orange, 457. And then I'm going to take that entire numerator and divide it by everything in the denominator. Notice that that entire thing gets square rooted as well before the division takes place under the numerator. So that is equal to the square root of, I'll move this equal sign out here a little bit. All right, note the brackets too. Number of data points is we have 7. The sum of the x squared values is our green value right here, 82,857. Okay. Minus the sum of the x's quantity squared. So that's the sum of our pink 733 quantity squared. Close that bracket. That all gets multiplied by what's over here. Number of data points is 7. The sum of our y squared values is the teal color, which is 29,921. From that, we're going to subtract the sum of the y values and then quantity squared. So the sum of the y values is this orange value down here, 457 quantity squared. Wow, eh? Now the safest thing to do when you're punching this in, of course, is to figure out what your numerator is and then finally divide by the simplified version of your denominator. You can do it all at once, but you got to be super careful in order of operations. I'm going to fast forward a little bit for you. If you do this properly, and you should try, because this looks easy but it's not, okay, one small press of a button can really mess it up. You should end up predictably with a negative R value because it looks like a negative correlation, and it comes out to 0.949, going to 3 decimal places. So, based on what we learned about in the previous lesson, we know that this R value is between -2/3 and -1. That means that in part C, where it says, what can the professor conclude about this relationship? Well, we can conclude that it is a strong negative correlation. Or in other words, that class size is strongly correlated with mean final grade, meaning that the larger the class size gets, because it's a negative correlation, the lower the mean final grade is. Now, this is a fictitious set of data. You can decide for yourself if that would actually be true. Does class size impact mean final grade? And then we can have a whole philosophical discussion about that as well. But nonetheless, this is a pretty cool tool. You should be able to do this with a table provided and with an equation provided. And you'll only have to do it a couple of times just so that you get an appreciation for the value of that R. And as I said, we will get into using Desmos to do this for us as well. So stay tuned.